From the intricate dance of atoms in a diamond to the elegant helix of DNA, the structure of matter dictates the properties of our universe. Understanding this hidden architecture is crucial to unraveling the mysteries of the cosmos, from the smallest particles to the largest galaxies. One of the most powerful tools at our disposal is X-ray crystallography. This technique allows us to peer into the heart of crystals and decipher the arrangement of atoms within. Imagine being able to see the invisible, to witness the fundamental building blocks of matter arranged in precise repeating patterns. X-ray crystallography allows us to do just that, revealing the beauty and complexity of the crystalline world. Like explorers charting unknown territories, we use X-rays to map the atomic landscape, discovering the secrets hidden within. This journey into the heart of matter begins with a simple yet profound phenomenon: diffraction. When waves encounter an obstacle, they bend and scatter, creating intricate patterns of interference. Think of ripples on a pond encountering a rock. The ripples spread out from the rock, creating a pattern of expanding circles. This is diffraction in action. In the realm of crystallography, our waves are X-rays and our obstacles are the atoms arranged within a crystal. When X-rays strike a crystal, they interact with the electrons surrounding the atoms, scattering in all directions. These scattered waves interfere with each other, creating a diffraction pattern. This pattern, recorded on a detector, holds the key to unlocking the crystal's atomic structure. Imagine shining a flashlight through a picket fence. The light rays passing through the gaps in the fence will create a pattern of bright spots on a wall behind it. The spacing and arrangement of these spots depend on the spacing and arrangement of the pickets. Similarly, the diffraction pattern produced by X-rays passing through a crystal reveals the arrangement of atoms within the crystal lattice. By analyzing this pattern, we can determine the distances and angles between the atoms, ultimately revealing the crystal's three-dimensional structure. To understand the diffraction patterns produced by crystals, we need a new way of visualizing their structure. This is where the concept of the reciprocal lattice comes in. The reciprocal lattice is a mathematical construct that simplifies the analysis of diffraction patterns. Imagine looking at your reflection in a mirror. The reciprocal lattice is like a mirror image of the real crystal lattice, but instead of distances, it represents planes of atoms. Each point in the reciprocal lattice corresponds to a set of parallel planes in the real lattice. The distance between these points in reciprocal space is inversely proportional to the distance between the planes in real space. This means that closely spaced planes in real space correspond to widely spaced points in reciprocal space, and vice versa. The reciprocal lattice provides a powerful tool for understanding diffraction. When X-rays scatter from a crystal, the scattered waves reinforce each other only in specific directions. These directions are determined by the spacing of the planes of atoms in the crystal, which are represented by the points in the reciprocal lattice. Now let's introduce another crucial element in our exploration of X-ray diffraction, the Ewald sphere. Named after Paul Peter Ewald, a German physicist, the Ewald sphere is a geometric construction that helps us visualize and predict the directions in which diffraction will occur. Imagine a sphere with its center located at the center of the crystal. The radius of this sphere is determined by the wavelength of the X-rays used. This is the Ewald sphere. The Ewald sphere provides a visual representation of the diffraction conditions. When a point on the reciprocal lattice intersects the surface of the Ewald sphere, it signifies that the Bragg condition is met for that particular set of planes. This intersection point corresponds to a diffracted beam in the diffraction pattern. The Ewald sphere acts as a kind of filter, selecting which sets of planes in the crystal will contribute to the diffraction pattern. By rotating the crystal or the X-ray beam, we can bring different points in the reciprocal lattice into contact with the Ewald sphere, revealing different aspects of the crystal's structure. Section 5, Ewald Construction, a step-by-step guide. Now that we understand the concepts of the reciprocal lattice and the Ewald sphere, we can delve into the heart of the matter, Ewald construction. This elegant geometric construction provides a step-by-step method for predicting and understanding the diffraction patterns produced by crystals. Here's a simplified guide to Ewald construction. First, construct the reciprocal lattice. Determine the reciprocal lattice of the crystal structure you are analyzing. Remember, each point in the reciprocal lattice represents a set of parallel planes in the real crystal lattice. Second, draw the Ewald sphere. Draw a sphere with a radius equal to 1 over lambda, where lambda is the wavelength of the X-rays used. The center of the sphere represents the origin of reciprocal space. Third, position the crystal. Imagine placing your crystal at the center of the Ewald sphere. The orientation of the crystal will determine which reciprocal lattice points intersect the sphere. Finally, identify diffraction spots. The points where the reciprocal lattice intersects the Ewald sphere represent the conditions for diffraction. These points correspond to the directions in which the scattered X-rays will constructively interfere, producing bright spots in the diffraction pattern. Section 6. Ewald construction in action, the simple cubic crystal. Let's consider a simple example to illustrate Ewald construction, the simple cubic crystal. This basic crystal structure consists of atoms arranged at the corners of a cube with one atom per unit cell. The reciprocal lattice of a simple cubic crystal is also a simple cubic lattice with the same orientation as the real lattice. Now, imagine constructing the Ewald sphere around our simple cubic crystal. As we rotate the crystal, different reciprocal lattice points will intersect the sphere, each intersection representing a diffraction condition. By analyzing the positions of these diffraction spots, we can determine the size and shape of the unit cell, and ultimately, the arrangement of atoms within the crystal. For instance, if we observe a diffraction spot corresponding to a reciprocal lattice point with indices 1, 0, 0, we know that the spacing between the 1, 0, 0 planes in the real crystal lattice is related to the distance of that reciprocal lattice point from the origin. Section 7. The power of Ewald construction, unlocking nature's secrets. Ewald construction is a cornerstone of X-ray crystallography, providing a powerful tool for understanding the structure of matter. By visualizing the diffraction conditions, Ewald construction allows us to predict diffraction patterns. Before even performing an experiment, we can use Ewald construction to predict the diffraction pattern that a particular crystal should produce. Index diffraction spots. Once we have obtained a diffraction pattern, we can use Ewald construction to identify which reciprocal lattice points correspond to each diffraction spot. This allows us to determine the size and shape of the unit cell. Solve crystal structures. By analyzing the intensities and positions of the diffraction spots, we can use Ewald construction to determine the arrangement of atoms within the unit cell, ultimately revealing the crystal's three-dimensional structure. Ewald construction has revolutionized our understanding of the world around us, enabling us to determine the structures of countless materials, from simple salts to complex proteins and DNA. Section 8. Beyond the microscope, the far-reaching impact of crystallography. The ability to determine the structure of matter at the atomic level has had a profound impact on numerous fields, including chemistry. Crystallography allows chemists to determine the structures of molecules, providing insights into their properties and reactivity. This knowledge is crucial for developing new drugs, materials, and catalysts. Physics. Crystallography plays a vital role in condensed matter physics, allowing us to study the properties of solids and liquids at the atomic level. This has led to the development of new materials with tailored properties, such as semiconductors and superconductors, materials science. Crystallography is essential for understanding the properties of materials such as strength, conductivity, and magnetism. This knowledge is used to develop new materials for a wide range of applications, from aerospace to electronics, biology, and medicine. Crystallography has revolutionized our understanding of biological systems, allowing us to determine the structures of proteins, DNA, and viruses. This knowledge is crucial for developing new drugs and therapies. The journey into the heart of matter, guided by Ewald construction and X-ray crystallography, has unveiled a hidden world of order, beauty, and complexity. As we continue to explore this microscopic realm, we can expect even more groundbreaking discoveries that will shape our understanding of the universe and our place within it.